Hello. Here we're going to solve the problems at the end of Chapter 6. This is the problems, the review questions, and the practice problems at the end of Chapter 6. Excuse me, let me get my calculator here. If you go to page 214 at the end of Chapter 6, we will see you'll see the review questions. We're just going to go over these very quickly. Question number 1 on page 214. What is a requirement for an object to be in translational equilibrium? In translational equilibrium, the only requirement is that the sum of forces, the sum of the forces acting on an object equals 0. To be in translational equilibrium. Now, number 2, distinguish between dynamic equilibrium and static equilibrium. As we talked about in the lecture, there can be two situations here. We have in the static equilibrium case, we have the case where the velocity of the object is 0. In the dynamic case, dynamic equilibrium case, we have that the velocity is some constant. It's not 0. But both these situations is to where, notice that the acceleration is 0. If the velocity is 0, the acceleration is 0. If the velocity is constant, the acceleration is 0. So in both these cases, the sum of the forces is equal to 0. Okay, number 3. What is tension? Tension is a force. Tension is a force, and it's given either in newtons or pounds, English or metric or English units, and it's the tension in a string or a rope or a it could be if you're in like engineering and you're looking at the tension along a beam, it would be the tension that's kind of going longitudinal through that element, through that beam, or through the string. A tension. Let me actually work. This is not an engineering class, but if it were an engineering class, there's two kinds of we haven't really talked about this yet, but since you're asking the question, I know you're wondering about this. If you have an element here, say this element is a beam, in the tension, we're trying to stretch that thing out. If this was a string, the tension acts to pull the string apart. You're pulling the thing in either direction. That's a tension. The opposite to that is compression, where you're actually compressing this. If this is a string, and you press the tension inward, the string is just simply going to collapse because it has no ability to withstand compressional forces, right? But if this were a beam, you could, say like a steel beam or a piece of wood, you could. And so we have tension acting outward and compression acting inward. But this is not an engineering class, so we don't have to deal with that. Let's see. Let me erase this. And number 4, review question 4. Which of these situations will result in most tension of the string? This is number 4. We have the A situation where the mass is held by 2 parallel strings. We have the B situation where the mass, it's the same mass, is held by two strings that are at an angle. So the question is, we have a tension 1 and a tension 2, and again, tension 1 and tension 2. Which is going to be greater? Well, in this situation, tension 1 and tension 2 will be greater than in these tensions will be greater than the tensions in the A case. Now, why is that? Because if you look at the sum, look at the sum of the forces in the y direction, both tensions, both vertical components of the tensions, T1 vertical and T2 vertical, outputs put in the y, have to equal the weight. Right? So that's true for both of these situations. But in the horizontal condition, notice that there's no horizontal condition here. So there is no horizontal, the sum of the there is no horizontal tension here. There's no horizontal force at all. But in this case over here, T1 horizontal and T2 horizontal have to add up to 0. So, which means that there is a horizontal component here, so the overall tension here has to be greater than the overall tension here. Okay. Question number 5. What is the difference between torque and force? Well, you know what a force is. A torque is simply a force acting on a lever arm to twist something. So if you have something you're trying to twist and you have a force that's out here and there's a rigid body here, a distance r away from it, say this is some rod, that is, and this is a force, it's a perpendicular force. The torque is this distance times the force. That is the torque, about, as we say, the torque about this point right here. So we can call this, if we call this a lever arm, we can. The torque is a force that's applied across some lever arm that's directed to some central point. Number 6, what is required for rotational equilibrium? What's required, if we wanted rotational equilibrium about this point, and this is F1, and over here we had F2, whoops, I should put it the other way, F2 about R2. In equilibrium, rotational equilibrium, the sum of the torques is 0. So the sum of this torque would be sum of the torque going clockwise is R1 times F1, and the sum of the torques going the other way, counterclockwise, which will give it a negative sign, counterclockwise, would be R2 force 2. And these have to equal 0. So this would be the static rotational equilibrium condition that must be met. Let's see. Number 7. Which of these situations results in more torque being applied? This is number 7. Number A or B? Well, let's assume, let me draw this. In the A condition, we have the force being applied this way. In the B condition, same radius, same force, but it's being applied at an angle. Which supplies more torque? This supplies more torque. This supplies more torque. Whoops. More torque. This supplies less torque because the perpendicular, if you look at the perpendicular here, this perpendicular is less than this one. So, okay, number 8. A mechanic tries with all his might to unscrew a nut. No matter how hard he tries, however, he just can't do it. What would you suggest the mechanic do in order to get the nut unscrewed? Well, he can't increase his force, but he can increase his radius, his lever arm, so he could simply get a larger arm over here, maybe a pipe, maybe a long pipe with the same force, and he would increase his torque. In fact, we use that technique all the time. If you have a hubcap or a lug nut on a car that you can't get off, put your crowbar or whatever on a long pipe, and you can usually get that lug nut undone. Number 9. Before cars came out with power steering, a big car required a much bigger steering wheel than a small car. Why was that? Well, it's because of this torque situation. A big car you have to produce more torque, so here's a steering wheel. If you can, with this, if you're trying to turn the wheel to the right, you would take your 2 hands and do this, but compare that to this situation where you have the same force, but a much larger radius. You can produce more torque here because this radius is larger than this radius. So this is able to produce more torque. Number 10, when analyzing motion on an incline like this, why do we split the forces up into components that are parallel and perpendicular to the incline? We do it in order to aid in solving the problems. As we talked about in the lecture, this object only moves parallel to the plane. Therefore, when we look at the sum of the forces that are parallel, it allows us to break up. Remember, the weight acts down, but what acts parallel here, if this is the angle here, what acts parallel here, this angle is the same as this angle here, and this is W, so what's parallel here is W times the sine of this angle. So we have the W times the sine of the angle acting down the plane. We can have a little bit of friction acting up, and that's equal to mass times acceleration. And perpendicular to the plane, there is no movement, so we know that the normal force acts up, and opposite that is the weight times the cosine of angle, and this is equal to 0, so it allows us to calculate exactly what the normal force is. So we break it up this way to ease in solving the problem. That's a very quick answer. Okay, let's now go over the review questions. We won't necessarily go over every one. These are the practice problems on page 215. Number 1 and number 2. Number 1 and number 2 are actually quite similar. So number 1 is actually in fact, they're virtually the same type of problem. Number 2 is a little bit more general. So let's solve them. I'm going to skip question number 1. I apologize about that, but I'm going to go over question number 2. It's actually quite similar. Okay, question number 2. Can you see that? Let's see. I think you can. A 15-kilogram sign hangs on a ceiling by 2 strings. What is the tension in each string? Basically, we have this situation. We have M and M is 15 kilograms, and we have a, this is T1, and this is T2. And this angle is theta 1 is 40 degrees, and theta 2 is 25 degrees. And the question is, what is T1 and what is T2, the tension? What are these two tensions? Okay. Well, first of all, we can look, do you remember from the lecture, we can look at the sum of the forces in the x and then the sum of the forces in the y. Okay, the sum of the forces in the x dimension will be T1 to the x, that's acting right, T1 to the x, I'll call this T1x, is acting to the right, minus T2x, T2, I'll just call it T2x, which is acting to the left. And the sum of those is equal to 0. This is a static condition. T1x is simply T1 times the cosine of theta 1 minus T2 times the cosine of theta 2 equal 0. It allows us to solve for one or the other. But we really need let's go ahead and plug, well, before we do that, that's the first equation. Let's look at the second equation. Second equation is the sum of forces in the y direction. Again, T1 in the y dimension, in the y direction, is acting up, plus T2 in the y dimension is acting up. These are the y dimensions of these tensions acting up, minus the weight, mg, which acts down. That's act down. So the sum of these plus the weight equal to 0. T1 here is T1y is simply T1 times the sine of theta 1 plus T2 times the sine of theta 2 equals mg. Okay? I'm going to, actually, when I'm going to come over here, I think there's room, and I'm going to solve for T1. We can say T1 equals T2 times cosine of theta 2 divided by cosine of theta 1. If you take this equation and solve for T1, solve for T1, move this to the other side, it's T2 cosine of theta 2 divided by cosine of theta 1. Okay. I'm now going to erase this top equation here. And let's go ahead and plug this into here. We're going to take this T1, or all of this expression for T1, and plug it right into this T1 here. And we get T2 times, well, excuse me, it's all of this, T2 times cosine of theta 2 divided by cosine of theta 1 times sine theta 1 plus T2, this is this term here, sine of theta 2, whoops, I better erase this, equals mg, which means that T2 times the expression cosine theta 2 sine theta 1 divided by cosine of theta 1 plus sine theta 2 equals mg. So I've factored out the T2 from both terms. At this point, I'm going to go ahead and just to plug in some numbers here. I'm going to solve for T2. T2 is, it's the mass, which is 15 kilograms, times g, 9.8 meters per second squared, divided by all of this mess here, all of what's in brackets. So we have the cosine of theta 2 is 40 times the sine of theta 1. Whoops, I think I got this wrong. Theta 2 is 25. Good thing I caught that. Cosine of theta 2 is 25. Sine of theta 1, which is 40. Cosine of theta 1, which is 40, plus the sine of theta 2, 25. It'd be very easy to get these angles mixed up here, which would change the answer. So let's make sure. Theta 2 is 25, theta 1 is 40, theta 1 is 40, theta 2 is 25. So the denominator here, well, the numerator, 15 times 9.8, is 147. What's in the denominator? Let's see. Cosine of 25 times sine of 40 divided by the cosine of 40, and I get 0.76048. I better check that. Let me check that one more time. Cosine of 25 times 40, the sine of that, divided by 40, the cosine of that. That's right, 0.76048 plus 25 times the sine of that, 0.42261, and if I add those up, okay, I get, these add up to 1.183, so I gotta do 147 divided by that the denominator, I get 124 newtons. And I need to, we have two significant figures, so I need to round that off to two significant figures. I would get 1.2 times 10 to the second newtons, or 120 newtons. So I would get, well, what is that, T2? T2 equals basically 120 newtons, and there's two significant figures here, the 1 and the 2. If I go back to this equation here, I can plug this, I can solve for T1. T1 equals T2, 120 newtons, times cosine of 25 divided by the cosine of 40. And here I would get 120 times 25 cosine divided by 40 cosine, and I get 140 if I round off to two significant figures. So this would be 1.4 times 10 to the second newtons for T1. And let's see. That's about, let's see. What I have here is the book. Looks like the book had something a little bit different. It may be round-off error. But what I have the book has is 150 and 130. I get 140 and 120. It very well may be round-off error, but you can check me on that. In any case, this is more or less how you solve the problem. Okay. Question number 3. Whoops. Okay, in question number 3, a 175 kilogram man weighs himself on a scale in an elevator. Number A, what weight does the scale read when the elevator is stopped? Well, he weighs 75 kilograms, so the weight when he's stopped is simply mg, which is 75 kilograms times 9.8 meters per second squared, and he would come up with 75 times 9.8, which is 735, or round off to 740 newtons. Okay, it's actually, I get 735, but I'd round it off to two significant figures. Okay, so that would be the answer for question number A, when the elevator stopped. Number B, the weight that he reads when the elevator is rising at a constant speed. When he's rising at a constant speed, again, he's going to read the exact same thing. There's no acceleration. If it's a constant speed, there's no acceleration. He's going to read the exact same weight, 140 newtons. Now, C and D is where the elevator is accelerating one way or the other. So, in this case, remember, if he's in an elevator, and the important thing is that the scale here, here's the scale, and here's the person standing here. The weight of the person acts down, but the normal force acts up. The weight acts down, and the normal force acts up. And the scale, remember, as you said in the lecture, the important thing is that the scale reads the normal force. The scale is really, in response, what the scale reads is really the reaction force, which is the normal force on the scale. And the sum of the force, and if everything is accelerating up a certain way, with a certain acceleration, the sum of the forces is that we have a normal force, normal force which acts up, we have a weight which acts down, and this is equal to the mass times acceleration, whether it's accelerating up or accelerating down. Therefore, the normal force equals to the mass times acceleration plus the weight, which is, so this is mass times acceleration plus mg, or we can say it's the mass times a plus g, where we simply add together the acceleration and the gravity. The acceleration can either act up or the acceleration can act down. The gravity, of course, always acts down. But remember now, we're saying that g is a plus 9.8, and we've taken into account of the negative downward direction with the negative arrow here. So if the acceleration is up, it's plus. If the acceleration is down, a is a negative number. Okay. So in number C, what weight does scale read when the elevator is traveling down and speeding up? Okay. If the elevator is going down but is speeding up, that means it's actually accelerating down, and so the acceleration is minus 0.95 meters per second squared. Okay. So it's accelerating down. So the a is going to be a negative number, which means, so if a is a negative number because the elevator is accelerating down. So the mass here is 75. This is number C, kilogram. The acceleration is minus 0.95 meters per second, and we add to that